Then for series, I'm not going to do as in-depth a review with series just because we have so much that we need to learn about series that we're going to be spending a lot of time on them. And the review can be spaced out because of that. So specifically, we're going to review an infinite series, which is the sum of an infinite number of terms. So we use the sigma, oops, so capital sigma to show that we're doing a series. We're adding up everything that comes after it. The bottom tells me what n is starting at. N's usually going to start at either a 0 or 1. Just make sure you're paying attention to which. And then because it's infinite, on top goes what it's going to, which is infinity. And then we're going to be given some type of explicit form to generate the terms that are being added. So it could be, I'm going to use just generic a to the n. So this means we're doing a when n is 0, plus a when n is 1, plus a when n is 2, plus a when n is 3, and so on. And then we do typically, in an infinite series, write the generic general term as part of this series, just in case somebody wants to generate, say, the 27th term that's being added. Common misconception here is that there is a relationship between a sequence and a series, but a lot of people think that the relationship is that an infinite series is just adding up an infinite.
I'm listening.
It's just adding up an infinite number of values in a sequence. But that's not what is happening. The relationship is actually that if I do the partial sums of an infinite series. So if I add, say, the first term, that's one partial sum. The first two terms, that's a second partial sum. The first three terms, that's a third partial sum. The first four terms, that's the fourth partial sum. And I keep doing this, and I generate a sequence of those partial sums. That sequence of partial sums is what we're looking at to decide, does the series actually converge to something? Because we're adding an infinite number of things, they're never actually going to reach a certain sum, but they can approach the sum. So in a geometric series, the terms that we're adding have a geometric relationship in that I'm multiplying by a common ratio to go from one to the next. So an example of that would be, let's say I have 1 plus a third, plus 1/9, plus 1/27. And it's me doing 1/3 to the n, which would be the sum where n starts at 0 and goes to infinity. It keeps going, of 1/3 to the n. That would be an example of a geometric series. Well, that converges if the common ratio's absolute value is less than 1, or you'll sometimes see it written as my common ratio is between -1 and 1, but can't equal those. With a geometric series, we can actually say exactly what it converges to. And it's going to be my first term over 1 minus the common ratio. And then if my common ratio's absolute value is greater than or equal to 1, then that means that the series would diverge. So some examples of this. I have the series where n is starting at 0 and going to infinity of 3 times 1/2 to the n. I have found it is helpful for me to actually write this out in terms of being able to see the sum, because I find it's a little bit easier to identify the different parts. So if n is 0, I have 3. If n is 1, if n is 2, if n is 3, that would keep going. There's my general term. Keeps going from there. I can now see that my first term is 3. My common ratio, well, that's times a half, times a half, times a half. So my common ratio is 1/2. And the absolute value of 1/2 is less than 1. So this converges to 3 over 1 minus a half, which is 6. So that sums to a value of 6. Then, if I look at the second one, what it looks like I'm doing is I'm doing pi over 2 to the n, because this is times pi over 2. This is times pi over 2. So my first term is pi over 2. My common ratio is pi over 2. However, pi over 2 is 3.14, etc., divided by 2, which is bigger than 1. So my absolute value of r is greater than 1, so this diverges.